Hello guys, welcome back to the third video of the binary search series. So in this video, we will learn about how to solve rotating, how to solve finding minimum element in a rotated sorted array. So basically, an array is said to be, uh, if you consider a sorted array, it is said to be rotated if some part of it is taken and moved, and some part of it is taken and moved to the other end. Like if we consider an array of 1, 2, 3, um, 4, 5, it is here in this case it has been break here, and this part is joined to the other side. So upon this kind of arrays are called as the rotated sorted array. So basically the array is sorted, and the some part of it is taken and joined to the other. So the point is here we have to find minimum element. So uh, if we see here, like um, if we see here in the rotated array, um, this 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 is probably solved in like linear search, but it is not that optimal, right? As we know that it will take big of n for searching for the minimum element here, or or simply the big of k, where k is the position of the uh, no, it will solidly take big of n. Since we cannot say that the specific k position is a minimum element, we have to iterate whole array. So but we can solve this using binary search in big of log n complexity. Uh, so let's see how we can solve this. Um, so I'll take low as usual. I'll take low as 0 and high as 4. Uh, High as 4 from this array since it's the relevant. So uh, now the mid value will be 0 plus 4 by 2, that is equal to 2. So it will be here. So if we check here, like the whole array is divided into two parts. So and the first part is joined to the back of it, like after the array. So there will be definitely there exists an element, an element which is smaller than both of its neighbors. There exists only one element which is like that, like it will be smaller than the left and also the right. So there will be only one element which is the minimum. Okay, so uh, if we consider here, um, we have to move towards the array which is such that uh, it will have a value. I mean, like we have to reduce the search space here. So my approach for doing this is like, if we consider the mid value here, um, let's just compare this with the end part. So here a of, suppose this is array is a, let's just name them. So a of m if a of m is greater than or equal to a of h, uh, if a of m is greater than or equal to a of h, this this case definitely says that a of m is not the smaller element, right? This is not the smaller element since it is greater than a of h, which is the smaller than a of m. So uh, in this case we have to move the lower value to m plus 1, because we have to reduce the search space. We have to reduce the search space to here. We can definitely say that the array, I mean, like the uh, required value will be here. I mean, the required minimum element will be here. So um, now we can consider that 3 plus 4, 3, 3 plus 4 by 2, um, which is the lower. Our next lower will be here, low. So 3 plus 4 by 2, that is equal to 3. That is 3. So this is, so this is our new mid. Uh, this is our new mid. So again comparing this, like 1 is not greater than or equal to 2. So in this case we will simply um, we will simply change h is equal to m, like we will get back, we are getting back. So ultimately, um, now in this case L is equal to H, right, till now. So L also will be here. So in this case, um, um, both L and H are at the same position. So give me a second. So basically, L and H are in the same position. So um, so if we again perform the operation, um, like mm, uh, mid value will be the again 3, but this time comparing with a of m is greater than or equal to h, it is equal. So we will get L is equal to m plus 1. So L will move to here. uh, since the terminating case of while loop is L less than or equal to h, uh, 4 is not less than h, which is 3. uh, 4 is not less than or equal to 3. So simply we will get out of this while loop of binary search. We will get out of this while loop of binary search, and after that, our h, our landing position h, um, will denote the minimum element value. H is index of minimum element, which is index of minimum element, which is the required solution. Index of minimum element. So this is the value we needed. Uh, let's um, let's just get into the coding part. I mean, this is the most what do we say? This is the most accurate solution I get into, like while solving this question. So let's get into the coding part. I guess you have understood the logic here. Like I'm taking the mid value and I'm comparing with this most right end, and if it is greater than the high value, then I'll reduce the search space to the right side. So I'll search in the right place. If it is smaller, like if the mid value is smaller than the higher value, then we will simply reduce the high to the mid itself. So upon performing this several times, uh, it will reduce the code to the usual part. So let's get to the code part now. Uh, Sorry. Um, let's just take int L is equal to 0. Everything is similar to uh, um, -1 point h. This is the terminating case, right? Okay. dm is equal to L plus h minus L by 2. If a of m, I mean num of m, is greater than or equal to num of h, then I'll simply I'll simply reduce the search space to L is equal to m plus 1, right? So in else part, in which case that nums of m is less than the num of h, then make the we'll simply make the h to m. So why I'm not making this to m minus 1? Since there is a chance that the element present in the h itself is a minimum element. There might be a chance, right? Since uh, yeah, there might be a chance that h itself is a minimum element. So I'll simply return uh, num of h here. I guess. Oh, sorry. I have taken this. Change. Okay. Num num start length. I'll simply change it to num. Okay. Yeah, it worked. So let's just run it to all the test cases. Okay, then code has been submitted. Yeah. So this is one of the way to solve this question, and that's it. Like this is one of the way to solve this question. There might be several ways, like finding the minimum element of its both neighbors. Like if you find a minimum element, then it will definitely be smaller than uh, both of its neighbors, like m minus 1 and m plus 1. So this way we can find, so this is one of the way we can find the minimum element. Like okay, if the element what we found is not the minimum one, like if the element we found is not the minimum, then we have to simply move towards this unsorted array. So parallelly this way we can solve this question. So okay guys, that's it for today, uh, for today's session. Okay, see you, have a nice day.